Hello and welcome to this session on the fundamentals of chromatography, where we will be describing the general processes involved with chromatographic analysis, which is specifically important to your instrumental and analytical chemistry needs. We won't really be covering any specific techniques such as HPLC or gas chromatography in this session, but we will be talking about general principles involved, including peak resolution and the various techniques which can be used to improve the quality of our chromatograph. So in the cases of improving our chromatographs, we're using a chromatographic medium to basically separate out the different components of our solution. It's all about reducing interferences. So oftentimes we have a sample we want to analyze, but there are various different compounds in there, and we want to know how much of each individual compound is present, or we just want to measure one of them. But unfortunately, due to overlapping peaks or interferences caused by the presence of other species, like as we've seen in previous cases with UV-vis spectroscopy, where the peak height and area can be influenced by other species, we want to remove those basically. And so chromatography is one of the ways of doing that. It can be as simple as doing something like a thin layer chromatography, where we have silica on an aluminum sheet, and then we just see the different components of our solution or mixture separate out as they move up the what's called the TLC, the thin layer chromatography plate. So usually whenever we do this, we have a strip like this. We cut it off a large sheet, and then we draw a line at the bottom, which is where we're going to place, call our origin basically. And we place a dot of our sample there. And then we would place this into a small jar with enough solvent to cover the bottom half of this, but not to come in contact with our sample. It's important that the solvent is in the jar, of course, but it should not be more than maybe about halfway to the point at which we deem to be the origin. Then, of course, over time, the solvent moves up through the thin layer chromatography plate, and it will bring with it the various different components that are soluble in that solvent. Eventually, we'll remove it before the solvent reaches the top, and the line at which it reaches, we will mark as well, and that will be called the solvent front. And then we can usually look at this under UV light or something like that, and we will see the different dots, and they will be present where they are. And then we can usually work out what they will be by running a pure sample TLC plate as well, and we will know like how far along the sample will move. And by and large, column chromatography is similar, only in column chromatography, we're able to sort of continuously remove sample. In the column chromatography, we're able to more easily separate our product from the reactants in mass. You can kind of do it with thin layer chromatography, but it's really for very small amounts. Now, whereas column chromatography can be used for quite a large quantity of material. So in column chromatography, we would have a glass column, maybe like this, and we're packed with silica in an organic solvent. So maybe like acetonitrile or something like that. Then we would place at the top our sample along with the organic solvent, and then that would pass through the packed silica column, and the different components would get separated out based on how quickly they're able to move through the silica. So that really depends on how much they interact with it. So if they don't interact very much, typically they move very fast through the column, but if they interact a lot, then they will be slowed down considerably. And this separation, as you can see here, it's quite clear. We have yellow, pink, and orange. Usually they're not that colored. Usually we have to run TLC plates for the different fractions that we extract and try and find out the ones which have our product in it and which ones do not have our product. So this is a glass column packed with silica in an organic solvent. Reaction mixture loaded on the silica bed with the help of a glass pipette. So usually up here at the top, we have our silica, we have to very carefully put the reaction mixture here so that we don't disturb the top of the column, which should be very flat. Usually we'll have prepared our column so that we'll have a very, very flat top part here. It's important that it's uniformly flat because otherwise there can be differences in the speed at which our products and reactants move through the column. And so it says here that chromatography is based on the difference in rate of movement of a solute through a stationary phase. The stationary phase here is the silica, which is on the metal plate. And here it is the silica, which is within the glass column. You can have different stationary media. You can have alumina, but usually we have silica. Then we consider the interactions between different species of atoms and molecules. So for example, silica is made up of silicon and oxygen. So there are oxygen molecules in there. So polar compounds are going to probably interact more with the silica than non-polar compounds. So non-polar compounds are expected to move through the column very quickly. And so we can make use of those kinds of differences in interaction to actually affect this separation. So what is chromatography? So many determinations involve separation followed by analysis. So chromatography, electrophoresis. Chromatography is a sample transported by the mobile phase. The mobile phase is the solvent. So usually what's happening here is that the different components of the sample are interacting with the stationary phase, the silica, by electrostatic or van der Waals interactions. And some components in the sample interact more strongly with the stationary phase and are more strongly retained. So they kind of stick to the stationary phase more. And thus the sample will be separated into zones or bands because some will move through very quickly and they'll accelerate ahead of the other components. Now, it really, it can be either way around. It can be like, for example, reactants move through fastest or products move through fastest. That's why we need to be careful and make sure that we run, or we only collect in batches so that we don't end up with a batch which contains both product and reactant. So we make use of these zones or bands in order to collect our sample of interest. So in chromatography, the mobile phase, the solvent moving through the column, is either a liquid or a gas. The stationary phase, the one that stays in place inside a column, is a viscous liquid chemically bonded to the inside of a capillary tube onto the surface of solid particles, or it can just be silica. So yeah, so the mobile phase can be a gas or a liquid. There's gas chromatography after all, and the stationary phase usually is pretty similar between liquid and gas columns. So the fluid entering the column is called the eluent, and the fluid emerging from the end of the column is called the eluate because it is eluted. So here is a kind of a schematic of what it might look like if we were able to shine a UV light on our sample. So we have a fresh solvent, the eluent, at the top here. And then, of course, we have a column down here packed with the stationary phase, which is suspended in the solvent. So it's important that before we add our sample, which contains both the wanted and unwanted components, it's important that we have a wet solvent or a wet stationary phase. The stationary phase should be filled with solvent and should not be dry in any part of it, because if there's a dry area, what can end up happening is that some of our, in this case, A or B can get stuck there, and it's very hard to remove it if it gets stuck. And at the bottom, there's like a glass porous disc. It's usually made from like more silica, basically. So it's made of glass and a glass fret, and it allows the solvent to pass through, any liquid components to pass through, but does not allow the solids to pass through. And then, of course, we have the solvent will come out the bottom. So we start off with A and B together, which have been placed very carefully on the top of the packed silica. And then as time goes by, they pass through the column, and we keep adding more and more solvent at the top, such that and we do it carefully so that we don't disturb the top of the column, such that it never gets dry, and so that it will continue to flow through here. And we can see the separation of the bands. Now, in reality, it's not always as clear as this, but you can see the general principle where we have them combined here. And then over time, as it flows through the column, A and B interact with the the stationary phase to different degrees. And so they get separated. So B in this case seems to interact less with the column than A does. And that's why A is slowed down or retarded in the stationary phase. And B continues to flow through. And then eventually this gap gets larger and larger until such times as we can collect all of B and all of A. So at this point, B is emerging and A is emerging here. So different types of chromatography. We have gas chromatography, as we've talked about, and liquid chromatography as well. And we also have a supercritical fluid chromatography, although that's quite rare because supercritical fluids tend to be quite hard to make. So, but it is possible. So gas chromatography, GC, is a gas liquid chromatography, GLC, or gas solid chromatography. So what does that mean? It's basically the gas is the mobile phase, and then this other one is the stationary phase. So in this case, it's a liquid, or in this case, it's a solid. The stationary phase is a liquid absorbed or bonded to a solid surface. That's in case of A, and in case of B, it's a solid. And then the type of equilibrium we have here is a partition between the gas and the liquid. And here we have adsorption of the gas onto the interface of the solid. In liquid chromatography, we have, of course, liquid partition. We have liquid solid or absorption methods. We have ion exchange, and we have size exclusion. And affinity liquid chromatography. So in these types of chromatography, for the liquid-liquid partition, we have liquid absorbed on or bonded to a solid surface. And so this was kind of the early form of liquid chromatography. And it was sort of based on the partitioning of the solute between two immiscible phases. And this is the major mode of retention. However, now in most liquid chromatography applications, it's really the molecular interactions, including things like dispersion, dipole-dipole, hydrogen bonding, charge transfer, ionic, as the major retention and selectivity methods. So that kind of leads us on to things like liquid solid or adsorption methods. And so the stationary phase here is going to be solid, because usually if it's liquid solid, that means liquid is the mobile, solid is the stationary. And then this is an absorption type method. So it's really due to the interactions between the solute and the sort of stationary phase. And we have ion exchange, which is an ion exchange resin. So we have ion exchange processes happening there. Then we have size exclusion, where we have liquid in interstices or polymeric solids. So this is kind of the idea of we're trying to only allow our solute to travel through a particular polymer. And so this is kind of similar to like a partition or sieving the material. And then affinity, we have a group-specific liquid bonded to a solid surface. And the partition here is between the solid, a liquid, and mobile liquid. Then supercritical fluid chromatography is another type of chromatography. It's not quite as common because at the end of the day, it's rather expensive to maintain. And so it's not really that industrially viable just yet. So organic species here are bonded to a solid surface. And the partition here is between the supercritical fluid and the bonded surface. So whether or not they want to be deposited on that surface of the stationary phase, or whether or not they want to be in the supercritical fluid. So in the case of column chromatography, we have a packed column here, which is usually filled with something like silica or alumina. Now the silica or alumina can be modified to provide differences in the retention times. So we obviously have our sample, which is placed very carefully on the top of the silica packed column, not to disturb that surface and keep it very, very flat. Sometimes sand is actually placed on top of there to try and protect the column, a very, very small amount of sand. Then we put our sample there. One of the ways that you can do it is you can inject it using a pipette, or you can actually deposit it on silica. Like you get your liquid sample, you put it together with some silica, and then you put it in a rotary evaporator, evaporate off the solvent, and then you have kind of like your A and B deposited on silica, and then you put that on top of the column. Then you're going to pass through various amounts of the mobile phase, the solvent. And over time, A and B are going to get separated. So in this case, A and B have different retention times. And so they move through the column at different times, at different speeds and rates. So the mobile phase is continuously added so that the column never gets dry. Then the A and B eventually get separated as they go through the column. So you need to make sure that in the length of your column, the two of them get separated with enough resolution that you can easily get fractions containing only A and fractions containing only B. Or if you're only interested in one of them, then fractions which contain only one of them. So over time, obviously A and B get separated out. Then the different fractions are going to be collected. So fraction at time 0, time 1, and time 2 will not contain any of A and B and will just literally be the solvent. Then at time 3, we're starting to collect A, and then at time 4, we are collecting B, and we line up a detector here at the end of our column so that we can see what it is exactly that's coming through. So here is a look at the different absorption detector signals for our samples as they come out at different times. So start off at time 0, which is whenever we add the sample, and then time 1, time 2, you can see that A and B are still in the column. And then at time 3, we have a peak which arises because of A. And then at time 4, we have a peak which arises because of B. And then you can see hopefully as well that the size of the A and B fractions is actually getting larger as they move through the column. So you can see here they start off at quite a narrow, and then here it's still kind of narrow, but here it starts to get, at time 2, it starts to get much broader. And then by the time they're coming through, it's actually very broad. This is longitudinal broadening. This is due to the interactions and of the A and B with the stationary phase. So one of the important things in chromatography and in the choice of how we do this, it's not just a case of any organic solvent will do and any silica will do. We need to make sure that our A and B, our reactants and our products are well enough separated that we can actually either measure their quantities or we can separate them well enough that we can then move on to the next step in our chemical reactions or even just get a pure product. So the peak separations then, so if like, for example, we have concentration of the species versus distance migrated, we have separation here in T1, a very poor separation where we have overlap of A and B. And so it would be quite hard to get all of A out pure. In fact, it would be impossible using this technique and this setup because the peaks overlap. And so there's a significant amount of A which will be contaminated with B. And of course, the whole point of doing this is to separate them out so that we get pure A and pure B. And you can see that in time T, we have a much better resolution, as it's called, because the peaks are well defined and quite separate from each other. They're a little bit close, so it would be a little bit, it would need a skilled operator to be able to separate these out perfectly, but it is definitely possible for T2, whereas at time 1, it's not really possible. So peak resolution is, of course, something which is going to be very important for us going forward and trying to separate out our components A and B. You can see here at the top, we have a setup which has got very poor resolution because the peaks are so overlapping that really it's hard to see even where the peak positions are. And then as we move through to B and C, we get better resolution there. So some of the techniques that we can use to improve peak resolution are to, for example, increase the separation between the bands in part B here. So you can see that the peak has been shifted so that the distance between them is further so that we can better separate out the two components. And then the bottom, we have less band spread, so we've created more narrow bands. This can be brought about through a number of different techniques. Maybe it's through changing the stationary phase, maybe it's changing the solvent. It just really depends on the individual analytes that we're trying to separate. So in all of this, we've been trying to find out how we can partition our analyte or our solute in our stationary phase, and how we can sort of manipulate the interactions between the different components of our sample with the stationary phase. And so this is related to a distribution constant or a partition coefficient between the mobile and the stationary phase, because remember, our analyte is in the mobile phase, but it may interact with parts of the stationary phase. And so it may momentarily precipitate out of the mobile phase and then back into the mobile phase. And this process can result in the sort of this changes in the speed at which it moves through the stationary phase. Now, so this is a partition, so it's an equilibrium, because remember that it can be absorbed either in the mobile phase or in the stationary phase. So A can be in either, and it just sort of depends on what local interactions it has, how much it likes to be on the stationary phase versus the mobile phase, because it depends really like how good its interactions are with either. So if its interactions are too good with the stationary phase, it's going to get stuck. But if it's too good with the mobile phase, then it's not going to interact with the stationary phase, and it's not going to be slowed down enough potentially. So there's really a balancing act here between the two. So Kc is what we will call the partition coefficient for this. And that's going to be equal to the concentration in the stationary phase over the concentration in the mobile phase. So Cs is then going to be equal to, so this is the concentration in the stationary phase, is going to be equal to the number of moles in the stationary phase over the volume of the stationary phase. And then Cm is going to be equal to the number of moles in the mobile phase over the volume of that mobile phase. So Kc in this is for low concentrations or when non-ionic species are present, and K is approximately constant whenever we have linear chromatography. So for K, whenever it's greater than, whenever it's large value, that means that we have more in the stationary phase. That increases the retention time. And we're asked, how do we manipulate K? Like what can we do to change the value of K? Because remember, K is a ratio between the concentration in the stationary phase and the concentration in the mobile phase. So when K is very large, that means that this number is much larger than this number. But if K is small, that means this number is larger, or this number is smaller than this number. So for example, if Kc is 10, that means you've got 10 times as the concentration in the stationary phase is 10 times greater than it is in the mobile phase. So how do we manipulate K? So retention times are, of course, dependent on how much the sample interacts with either the stationary phase or the mobile phase. If it's very much in the mobile phase, it will move through the column very quickly. But if it moves, it's retained very strongly by the stationary phase, it will move very slowly. So Tm in this figure here is the retention time of the mobile phase. So this is kind of like how long it takes for the mobile phase to move through the column. Now, whenever we're doing a packed column, we've seen for separation of components, there is limited dead time because we're already starting with a column which is saturated in solvent. But if we're doing things like HPLC or gas chromatography, then those techniques do have a dead time, which is the time it takes for the mobile phase to pass through the column. And so this is sort of when we start our T0, whenever Tm passes through, and then we measure from that point onwards. Of course, time is being measured continuously, but this is how we start the basis of what Ts is going to be. So Ts is the time spent in the stationary phase. So obviously it starts off in the mobile phase whenever we inject our solute. It's in the mobile phase. But then after that, it spends some time in the stationary phase, which is Ts. And so in order to find Ts, it's going to be the starting at time m. So say, for example, it takes 1 minute for the mobile phase to pass through the column. Then after 10 minutes, our analyte comes through, our solute passes through, and we detect it using our detector. This is detector signal on the Y scale. So that would mean that we would have a TS of 10 minus 1. So our time in the stationary phase would be 9 minutes. Now, this may be very long, but it's just an example. And then the total retention time of the analyte or the solute would be 10 minutes. And L is just going to be the length of the column. Usually it's about 30 centimeters. So chromatography velocities. So the velocity is obviously equal to distance divided by time, or column length over retention time. So the column length here would be the height of the packed column, the silica part. So the velocity of the solute then is going to be equal to the velocity is equal to the length of the column divided by TR being the total retention time from injection to it coming out of the column. And then the velocity of the mobile phase is going to be equal to mu, which is the velocity of the mobile phase, is equal to the length of the column divided by Tm obviously being the amount of time it takes from injection to it coming out of the column at the bottom. So that would be mu, the velocity of the mobile phase. So the velocity then of the solute is going to be equal to mu times the fraction of the time spent in the mobile phase. So earlier we said this was 1 minute. This was then 10 minutes here. So that would be 1 over 10 because the total time was 10. So this would be 1 over 10. So the velocity is equal to mu times the moles of solute in the mobile phase divided by the total moles of solute. And then that can be related to this, which is then the velocity is equal to mu times the concentration in the mobile phase times the volume of the mobile phase over the concentration in the mobile phase times the volume of the mobile phase plus the concentration in the stationary phase times the volume of the stationary phase. So we have this form now where the velocity is equal to mu, the velocity of the mobile phase, times this term, which takes into account how the solute moves through the mobile and stationary phases. This can then be sort of rearranged to give us this form. And then since we know K, where we have the concentration of the stationary phase divided by the concentration of the mobile phase, we have the distribution constant, which is K. And then we can substitute that in because we know that CS over CM, which we have here, is equal to K. And so the velocity then becomes equal to the velocity of the mobile phase times 1 over 1 plus K times the volume of the stationary phase divided by the volume of the mobile phase. And so these are some of our velocity mathematical relationships, which will be important for us to work out how fast our solute is moving through the column. So this is the equation we had on the previous slide, and then Ka is the retention factor. So that's going to be equal to Ka times Vs over Vm. So Vs is the volume of the solute of the stationary phase, and Vm is the volume of the mobile phase, and Ka is the partition coefficient of our analyte or the species that we're interested in. So this retention factor then is going to be substituted into this. And so we then get the velocity is equal to the mobile phase velocity times 1 over 1 plus Ka, the retention factor. And then that can be related back to the length of the column, because remember that the velocity is the length of the column divided by the total retention time. So if we go back, I can show you. So back even further. So the velocity of the solute is equal to L over TR. And see, L is the length of the column. TR is this distance, the total retention time. So from injection to the solute coming out. So here, so that is equal to mu, which is the length of the column times the time of the mobile phase coming out times 1 over 1 plus Ka. And then Ka, then if we rearrange this, is going to be equal to Tr minus Tm over Tm. And so this is the adjusted retention time. Okay. Remember, L disappeared here because we can divide through by L, and we'll lose it on both sides. So relative retention time, then the use of the relative retention time, RRT, reduces the effects of some of the variables that can affect the retention time. RRT is an expression of a sample's retention time relative to the standard retention time. So RRT is equal to TR, which is the total retention time, divided by TRS, which is the retention time of the internal standard. So sometimes we use an internal standard, which we know very well the interactions of. So it's well established how long that might take to come out. The selectivity factor is going to describe how much the system selects for a particular component. Either if we have a mixture of A and B, it's sort of like how much more is one of A or B retained compared to the other. So basically which one is going to be retarded more. So if B is retained more in the stationary phase than A, then alpha is going to be greater than 1. But if it's the other way around, then it's going to be less than 1. So alpha is the selectivity factor. So that's going to be equal to the distribution coefficient for KB over KA as a distribution constant. And then we have also got a selectivity factor for the retention factor where it's KB over KA again. And then since of course we have KA is equal to the total retention time of the analyte A minus the total retention time of the mobile phase over TM. And then we do the same thing for KB because remember we could have a system where it didn't work out very well. So this is the mobile phase coming out. Then we have A, and then we have B, or it could be B and then A. So this would be M, this could be B, this could be A. So we have a retention time T R B, and then we have T R A is the time for A to come out, which is this one, B to come out, which is this one. And of course we have our TM, which is this one. So then the selectivity coefficient can be expressed like this, because at the end of the day, we have expressions for Ka and Kb. We substitute them in here. So it's related then to do with the retention times of the different species. And so all we need to know is the time it takes for each one of these to come out so that we can get the selectivity factor. So for example, we put in the value for TB. So like, for example, if the stationary mobile phase is 1 minute, takes to come out, then B is 5 minutes and A is, I don't know, 10 minutes. Then we can fill it into our retention time calculation. So alpha is equal to TRB, which we've said is 5 minutes, minus TM, which is 1, all over TRA, which we said is 10 minutes, minus 1, which is the time it takes for the mobile phase to come out. So that would be 4 over 9, which I didn't choose my math very well, but basically this would be the selectivity coefficient. And so that would indicate that A is retained more than B. Because remember, we said up here, if B is retained more than A, then alpha is going to be greater than 1. Column efficiency then is sort of like the number of molecules that come through in a certain length of time. So here the column is divided into something called a theoretical plate, where we kind of separate the length of the column into a certain number of imaginary plates that kind of describes how the sample moves through the column, where H is the plate height, N is the number of plates, and then N is equal to the length of the column divided by H, which is the plate height. So it's basically a number of divisions of the length L, where L is the length of the packing material. So from sample in, the injection site to detector is given this value L, and then the distance migrated is obviously given here in terms of the distance between the sample in and the detector. So here we have the sort of Gaussian distribution of the number of molecules observed around the detector, where we have a distribution around the L value, which is where the detector is situated, and the column height is related to the standard deviation of the distribution of the molecules around this central L point, where the distance between these lines is given as L plus 1 standard deviation and L minus 1 standard deviation. And so the height then is equal to H is equal to the standard deviation squared over L. So this is a distribution of molecules that comes through. And so it's related to the peak, which is observed as it comes through, because remember, this is usually a UV vis absorption detector. So what's happening is we get different absorption values as the number of molecules increases. So initially we've got a few molecules of our solute passing through, and so therefore we have a lower absorbance, and then this absorbance increases to a peak at a certain point and then decreases again. And there's usually a very nice Gaussian distribution. And so from that Gaussian distribution, we're able to get the standard deviation, and the standard deviation is used to calculate the plate height. So H is equal to the standard deviation squared divided by L, where L is the length of the column packing. Standard deviation is given there as sigma. Sigma squared over L is then going to be the variance per unit length. So here it is again, but this time we now are taking into account the width of this peak here, and then the time retention TR, and then the time for the mobile phase to pass through the column as TM. And so we can then relate all of these together to find out the column length, the standard deviation and distance, TR, the retention time, tau, the standard deviation and time. Then we can relate these. So the height of the, standard deviation over L is equal to tau over TR. And so then tau is then equal to sigma over L over TR. So sigma is the standard deviation and distance, L is the length of the column, and TR is going to be our retention time, the total retention time. So it's like from the injection point to the peak maximum of our analyte profile. So then here it is again, the same thing. This time though, we're taking this new equation we have, and then we're now translating it into terms of the distance standard deviation. And then we now have a new term for the width here. So the width here is usually going to be 4 times the standard deviation of the time. And then sigma, then we can put this, okay, so sigma is going to be equal to tau L over TR. So then if we have a term for the width, this W value, as being 4 times the standard deviation of time, then we can put that into our expression for the standard deviation in terms of distance as WL over 4TR. And then the plate height then, because we know sigma can be substituted in here. And so we can find out the plate height quite easily from the values that were given, just quite normally actually readable from the chromatogram. So what we've really done here is we've gotten a term for sigma, which is in terms of the peak width at the bottom, so the peak width here, L then being the value for the length of the column, 4 coming from the W term here, and then TR being the retention time from here to here. And so then we can calculate reasonably easily the plate height in H. So then we can get plate height H in terms of sigma squared over L is equal to W squared L over 16T R squared. So that gives us a more manageable term for plate height. Then determining the number of theoretical plates. So N is the number of plates, as we know. 16, so this is using this equation we had on the previous slide where we put N into our equation that we had earlier. And then we find out that the number of plates is going to be equal to 5.54 times this TG over the half of the width of, the peak width at a half maximum. So if the maximum here is 1, we would take it at 0.5. We'd find the width of the peak at 0.5. And that will be how we would find the number of plates. Okay, so plate theory successfully accounts for the peak shapes and rate of movement, does not account for the mechanism causing peak broadening. It doesn't explain why peaks get broader, basically, but it does successfully account for the shape of the peaks and the movement involved. There's no indication of other parameters effects, and there's no indication for adjusting experimental parameters. So it doesn't tell us, it explains the peak shape, but it doesn't really tell us what we can do to improve or change the peak shape. And so that's one of the issues with plate theory, although it is the basis for rate theory, which is much more widely used. So rate theory includes that zone broadening is related to the mass transfer processes. So rate theory is based on plate theory and carries over some of the advantages there, where it can reasonably well account for the shape of the peaks, but it also brings about the idea of zone broadening. So like the width of the peak or the shapes of the peaks is related to the mass transfer processes. The kinetic variables then are shown here. So we have linear velocity of the mobile phase. So that's just the speed at which the mobile phase moves through the column, and that's given the letter U. Diffusion coefficient in the mobile phase is dm. Diffusion coefficient in the stationary phase is ds, and they're given the usual units of centimeters squared per second, centimeters squared per second. Retention factor is K, which is unitless. Diameter of packing particles is dP. Thickness of the liquid coating in the stationary phase is dF. So this is the liquid coating of the packing particles. So these would be the stationary phase particles. Because we're going to talk about the efficiency of our columns, the efficiency of our chromatography, and then we're going to consider reasons why efficiency may vary. So here we have a zone broadening where we have a flow rate of the mobile phase in both liquid and gas chromatography. So we see a similar shape here where at low flow rates, we have maxima in the efficiency. So that would be where H is the smallest. So both of them happen at low flow rates, but if you notice, there is going to be a slightly different flow rate for both of them. So the flow rate, whilst both of them are at low flow rates, the flow rate for liquid chromatography is about 2 orders of magnitude less than that for gas chromatography. So you can see the minimum happens around about 20 centimeters per second in gas chromatography, or about 0.2 centimeters per second in liquid chromatography. And so this is due to the sort of like the retention factors of the stationary phase, the generally higher interactions of the liquid phase with the solid stationary phase and things like that. Also, usually gas chromatography is much more efficient than liquid chromatography. It has better resolution, it has better flow rate, better output rate, but sometimes you can't get both at the same time. In liquid chromatography, it's very difficult actually to get this kind of efficiency because the flow rates here are too slow, and the flow rates are usually much, much faster than this, which results in there being a reduction in the efficiency of our column. So the column efficiency can usually be somewhat similar to the gas chromatography, but we cannot get the that kind of efficiency with the flow rate that usually is seen in practical applications, because this is very slow. So it would take a very, very long time for us to process our samples. So one of the things that can happen is our kinetic processes, which happen within the chromatography column, and it can be, the efficiency can be described pretty well by this Van Deemter equation, where we have H, which is the height, is going to be related to A, which is the multiple flow paths. So that whenever we have the bed of the stationary phase, there are going to be multiple different paths that it can take around the particles. Then we have B over U, which is the longitudinal diffusion through the column. So basically just the diffusion of the particles through, or the liquid through the solid. And then we have here the mass transfer to and from the mobile phases, or between like the to and from the stationary phase, CS, to and from the mobile phase, CM. So the Van Deemter equation describes chromatographic efficiency. Lambda and gamma, are constants that depend on the quality of the packing. So they're seen over here. B is the coefficient of longitudinal diffusion, and C, S, and Cm are coefficients of mass transfer in stationary and mobile phases. So you can see here, lambda here is related to the quality of the packing. So it's really very important that we pack the column well in a practical sense to get the maximum efficiency out of the column. So this really models the efficiency of a column very well. A lot of effort has been put into creating quantitative relationships between the observations in chromatography and the processes that are going on. So it can really well model these sorts of processes. So you can see here the different components. So H is the overall efficiency, which we saw with the liquid and gas earlier. And these are the different components and how they contribute to H, the efficiency. So we have B over U, we have CMU, and we have CSU, and how those add together basically to form this H here. So the Van Deventer equation, as we said before, lambda and gamma are constants that depend on the quality of the packing. B is the coefficient of longitudinal diffusion. CS and Cm are coefficients of mass transfer in stationary and mobile phases. So zone broadening, so this is where we have the multiple pathways. So this comes into that A term that we talked about earlier. There are multiple, if we have, for example, we started a frontier A and then we're getting to a frontier B, we have two particles, 1 and 2, that start at A, but they can take different paths going through the solid phase. So you can see here, 1 has a more direct route than 2 does. And so we would expect that particle 1 would reach B first if they're identical particles, because 2 would have a greater degree of interaction and it would just be more difficult for it to pass through there, which is why the efficiency of packing is so important, because what ends up happening is that if we have a very efficient packing, so that means it's very even throughout the column, what's going to end up happening is that most of the particles are going to travel through together and we will improve the appearance and the quality of our resolution. So eddy diffusion is the band broadening process that results from different path lengths passed by solutes. So if we have 3 different particles. At the start, they're all together. They haven't passed through the column yet, but each one of them takes different path lengths. So one has a path where it passes through very easily and it gets there first because the path that it takes is very direct. And so it would have less of a sort of an eddy and sort of a random path, the way that particles 2 and 3 would have. So directly proportional to the diameters of packing, eddy diffusion. 2, offset by ordinary diffusion. And 3, lower mobile phase velocity means smaller eddy diffusion. So stagnant pools of mobile phase retained in the stationary phase. So basically, if there are large sort of gaps in the stationary phase, then these will fill up with the mobile phase, and that will sort of reduce the velocity of the mobile phase through the stationary phase. So that's why we really need to make sure that it is well packed. So zone broadening, longitudinal diffusion. So higher the velocity through the longitudinal velocity means a smaller h, which h is the efficiency, that also the plate height. So much smaller in liquid chromatography than gas chromatography. This is the Van Deventer equation that we saw earlier. So we start off with this band here where our solute is inside of the column. And then after some time, we see that there is longitudinal diffusion as described by B over U. And this zone of the solute has increased in size. And this is related to this term in the Van Deventer equation. And this is just due to like the different paths that they take. Some are longer, some are shorter, and the different solute molecules get spread out. So we have here, for example, the mobile phase as it's passing through. We have mass transfer between the mobile and stationary phase. This is rather simplified version of that. So what's happening here is that we have particles which diffuse into the stationary phase. So they kind of are associated with the stationary phase. They kind of stick there momentarily. And we have them then diffusing back into the mobile phase. So they diffuse in and out, and this is due to their intermolecular interactions. So in this one, we have fast mass transfer relative to the mobile phase velocity. So what happens is that the frontier does not really like extend. And here we have slow mass transfer relative to the mobile phase velocity. And so what happens is that some of the particles kind of get left behind and they get spread out. And so this ends up increasing the width of the peak. So slow equilibrium of solute between the mobile and stationary phases causes a broadening of the peak, whereas fast keeps the particles generally together. And so this mass transfer is the time is required for solute to diffuse from the mobile phase to the interface. So mobile phase into the stationary phase and back out again. So longitudinal broadening versus mass transfer, how do they differ? So longitudinal is parallel to the flow and inversely proportional to the flow of the mobile phase. So longitudinal broadening is inversely proportional to the flow of the mobile phase. And then for mass transfer, diffusion tends to be at right angles to the flow. So it's like, going to be like, so if the flow is, like this, then at right angles to this means the diffusion is going this way and then back out again like that. Okay. Larger the difference between the mobile phase velocity and solute diffusion, the larger the band broadening is going to be. Okay, so resolution is a big thing in chromatography because it allows us, as we've seen, to separate the peaks better and to get a better sort of understanding of the quality of the chromatogram. And also eventually it's going to allow us to work out how much of something is there or to separate the two components better. So these equations measure the resolution. So the resolution is RS. And so that's going to be equal to delta Z being the separation between the peaks. So here you can see the peak here and here. That's delta Z here. WA is the width, or WA over 2, sorry, is the half width of the peaks of peak A and peak B. So we can see over here that we have WA over 2 is half of the peak at the base. So WA is the base of A and WB is the base of B, this one. So we're looking at WB a half, but we could just multiply this by 2 and we would get the resolution as 2 delta Z over WA plus WB. And so then we can then substitute in delta Z for the retention times that we have measured. So, I mean, you could measure the distance here. It's not that difficult, but if you only have the retention times of A and B, you can also use that. So that would be 2 times the retention time of B, assuming B goes through faster than, or sorry, slower than A, then the retention time of B minus the retention time of A, all over the width of A plus the width of B. And so those are our equations to measure the resolution of our chromatography, our chromatogram. So here we have a general elution problem. So we have a mixture of these three different pairs of components, and we need to try and separate them in some manner. So we have a couple of different options. So A, we see that there is pretty good separation between each of the peaks, but it takes a long time to sort of elute them. So it would require quite a lot of solvent. B, we can see that there's poor resolution between 1 and 2, and 3 and 4 because they're overlapping. 1 and 2 basically form one peak. But 5 and 6 are pretty well resolved, and they're moving through the column pretty well. And then in version C, we have a pretty good resolution between 3 and 4 and 5 and 6, but 1 and 2 again are proving to be a problem. So overall, we kind of see that there is, at least with these components, a great difficulty in resolving them effectively, because in A, 1 and 2 are well resolved, but 3 and 4 and 5 and 6 are not well resolved at all. 3 and 4 are can be, we can deal with 3 and 4, but 5 and 6 have got very poor signal, and so they could not be defined unambiguously, because they're just not, it's very shallow, and like their intensity is very low. Of course, here in B, we have well-resolved 5 and 6, but the others are not well-resolved at all. And C, the time is very long, and so it would be problematic to actually run this. But 3 and 4 are well-resolved. 5 and 6, they're okay, but not really that, it's not really what we want. 3 and 4 this is the kind of standard that we want for here, 3 and 4 in C, 5 and 6 in B, and 1 and 2 in A. And you can see this is a standard problem in chromatography, is how to separate everything well without compromising the other components. One of the ways that you can do this is by an ingenious method of multiple passes through a column. So this column has been set up with a valving system where the components can be passed through the column multiple times, and the resolution can then increase well. So see here that the first pass, there's very limited separation, which improves the number of passes that we make until we get to about 10, and we have a resolution of about 1.5, which is sort of the minimum standard for what we can accept, is about 1.5 for our RS value. And so you can see that then as the resolution improves as the square of the number of passes, or the number of passes, sorry, is proportional to the square of the resolution. So longer column, more pass-throughs improves resolution. So yeah, we're not having a very long column here. We're just using the column multiple times. So it's effectively the same as increasing the column length. So the retention time relationship then is also responsible for some changes in our resolution. So a Purnell equation governs the resolution of two closely spaced symmetrical peaks. The resolution is equal to the square root of n over 4 times alpha minus 1 over alpha times k2 over 1 plus k2, where n is the number of is the number of peaks, number of plates in the second peak. Alpha is then the separation factor, and K2 is the retention factor of the second peak as normal. So the equation highlights which factors can be changed to vary resolution. So if we have the initial chromatogram here and we increase K, we see that we get resolution, but the elution time increases. If we increase alpha, we can see that we get a good separation. Well, it's not really compromising on time, but the peaks do tend to broaden a little bit, and then increasing the number of plates does not significantly improve the resolution because we still have an overlap of the two peaks, although they do become more narrow, and so we do get a faster elution time. So here is some of the effects of changing the solvent mixture and how great of an effect that can have. So in run A, where we use 70% methanol, 30% water, mobile phase, we see that it's really just a jumble of peaks. There's no real way to kind of separate the peaks here. This is the injection point, and these are the peaks. They're all jumbled up, and there's no resolution there at all. But we can see that by changing and increasing the concentration of water in comparison to methanol, we've been able to at least resolve and see how many peaks that we have. We have, in fact, 5 peaks. And by continuing that into C and D, we can see that increasing the water concentration improves the separation greatly. We have here in C probably the best, which has a pretty good separation between all of the peaks. And we can see that if we increase water again, we end up with really good separation between peaks 1 to 4, but then peak 5 becomes kind of unidentifiable. And so that's problematic, especially if we want to accurately determine number 5. So this really just sort of highlights how important the choice of the mobile phase is. There are many variables going on in chromatography, and it's not always obvious which one it is that we need to pursue. So chromatographic definitions then. So this is sort of a cheat sheet, I guess, for this. So we have migration time on retained species is TM. So this is determined from the chromatogram. Retention time for species A and B is given here also from the chromatogram directly obtained. We can get the adjusted retention time for A, which is given here. as the retention time minus the mobile phase time. Peak widths for A and B from the chromatogram as well. Length of the column is L, that's direct measurement. Volumetric flow rate, F, direct measurement as well. Linear flow velocity, U, from F and column dimensions. Stationary phase volume from packing preparation data. So we know the diameter of our column most likely, and we know the height of it, so we can work out what the volume of the stationary phase is going to be. Concentration of the analyte in mobile and stationary phases here is from the analysis and preparation data. And then here are some of our equations. So linear phase velocity, U is equal to the length over Tm, where Tm is the mobile phase time. Volume of the mobile phase is given here. Retention factor then as well, given here the retention time of the different species, Tr minus Tm over Tm. It also has a relationship to this, which is the volume of the stationary and mobile phases combined in an equation. Distribution constant here, selectivity factor here, alpha resolution, then is given like so, but there's also another way from the Purnell equation to calculate the resolution where we have n as the number of plates of the second peak. Then we have the selectivity factor, and then we have the retention factor here of the second peak, which would be B. Number of plates then be calculated like this. So that's the peak width, and this TR is going to be the retention time. It's related also to this equation where we make use of the selectivity factor and the retention factors. Plate height then, H is equal to L over N, and then retention time is given here in this equation where we have the resolution, and we have H, the plate height, U, which is the linear mobile phase velocity, A, the selection coefficients, and KB, the retention factor of the second peak. And don't forget also the Van Deemter equation that we saw earlier. And so that's kind of an introduction to the fundamentals of chromatography. Thank you for watching.